Hi everybody. We are going to start off on Desmos today because I would need to show you how we're going to deal with a different type of transformation. To remind you of the transformations we've done so far, right now you're looking at a graph of just a simple sine curve. I've got a few different sliders over here. It's actually something times sine of something times x right now. And so we saw that a in the front, the coefficient on the front, changes the amplitude. Right now the amplitude is 1 because the coefficient in front is 1. But if I make the coefficient 2.85, now the amplitude is 2.85. If I make that number negative 4.3, the amplitude is 4.3, always a positive value for the amplitude. And then we also saw that if I have a k value, something multiplied by x, right now k is equal to 1, so our period is 2 pi, and we can see that on the graph here. Actually, I'm going to change this. No, I take it back. I'm going to leave it as it is for reasons that don't matter too much just yet. But we can see that 6.28, 2 pi is about right there. That's what the period is right now. And if I make that number larger, if I make that number 2, now the period is 1 pi. If I make that number smaller than 1, now the period is, well, whatever 2 pi divided by 0.6 is. And it makes it bigger. What we need to take a look at today is what happens when it's not just x or something times x, but I'm going to do k times x minus c. And I've got a slider for this one also. Right now the value of c is 0, so it's k times x minus nothing. So the graph hasn't changed by me doing that. But I want you to see what happens when I now change the value of c. And I'm just going to slide it around right now so you can see what's happening. And this is a horizontal translation, or a slide. And we notice that if that value is a positive, now we've got to be careful because we are subtracting this number. So this would look like sine of x minus 5.2. And we can see that it moved over by, let's see, it was crossing at the origin. When I move it to, let's stick with 5.2, that point where it was crossing moved over here. It looks like it moved over by about 5.2 or 5.24, I guess. So it looks like that's the value that it changes by. Here's the big issue. If I change my k value, I'm going to make it k equals 2, a nice whole number. Now I want you to watch what happens as I move this. Now I'm going to move it from 0 to 1. What happened is it didn't move over by 1. It moved over by, take a look at where it is. And as I move it over by 1, we see that it moved over by, it looks like about a half instead of 1. If I make my k value larger, if I make my k value, let's go all the way up to 5. This is tough to see, but if I move from a c value, I've got 5x minus 0 right now, and so it's crossing. The sine curve crosses at the origin. It's increasing at that point. Watch how far I have to move this over before it has moved up by 1 spot. That point right there is where it crossed before, and it's moved over 1, even though my value of c, the number that's right here, I had to go all the way up to 5 to do that. Seems like there's no pattern to this, or if there is a pattern, it's hard to figure out. Here's the trick, and here's the reason I'm doing this on Desmos right now. I'm going to move this c value back to 0. I'm going to stick with the k value of 2 because I think that's going to be a little bit easier for us to see. But I'm going to change the form of my equation. Instead of kx minus c, I'm going to put that x minus c in parentheses. I'm going to call this the factored form. This scale factor, that k value that determines our period, has been factored out of the parentheses. And so now, watch what happens when I move the c value. If I make it 2, the graph actually moves by 2. That point where it was crossing the axis, now it's crossing, and I think I can even do this on Desmos. That point is now at 2, 0. If I slide it over by 5, now that point where it was crossing the axis has moved over by 5. This is extremely important. I'm sure I'll repeat it once I get back to the notes and do the problems. But if I want to see this this change, this, we're going to call it a phase shift, this equation needs to be in factored form. Otherwise, the number that shows up here, this number c, does not represent the phase shift. And everything works the same over on the negative side. I'm going to refer to this as a negative phase shift or a phase shift to the left, but also keep in mind that now I've got a negative value for my c, and it's also being subtracted. So in the equation, x minus a negative number is going to look like x plus. And so moving to the left comes from x plus a number. Moving to the right is going to come from x minus. Because of the way I've got this set up, notice it's really nice. As the value, oops, I didn't want to do the k value. As the value of c gets bigger, it's moving to the right. As it gets smaller, it's moving to the left. And that makes sense. If this was a plus, this is going to be counterintuitive. As the c value gets bigger, the graph is moving to the left. And as the c value gets smaller, the graph is moving to the right, which is backwards of what we would like to think, which is why we put that negative there. The problem with that is that we have to keep in mind we're subtracting either a positive to move to the right or a negative to move to the left. Okay, let's hop over and see some examples. So we've got a general form for an equation that looks like this. Y equals something times sine, or cosine, by the way, sine or cosine of something times, and then here's our factored form, x minus c. In this form, the value of a, or actually I suppose the absolute value of a, there's our amplitude. The period, this is from last week, we saw that 2 pi divided by k, that determines the period. Or I suppose if we've got a degree problem, we'd have to do 360 divided by 2k. 360 we handle equivalent to 2 pi, 360 degrees over k, depending if we're in degrees or radians. And then what we just saw in Desmos, the horizontal shift, I call it the phase shift, is the value of c. If in the equation we're considering that it's x minus c. So if I have x minus 5, the phase shift is 5, positive 5, 5 to the right. If it's x plus 5, then the phase shift is either left by 5 or negative 5. So we'll keep that in mind as we are doing some of these problems. I'm going to try to go efficiently and quickly through these, but also I want to make sure that I'm explaining. So I'll try to balance it so you don't end up with a 75-minute video, but I also don't want to go so fast that people are confused. So if I do a good job, then hopefully this works. Here's our first equation. I've got 2 times cosine of x plus 90. Amplitude is 2. Period, because there's no number multiplied by the x, the period is either 2 pi or 360, but since my phase shift is in degrees, it must be a degree measure, 360 degrees. And then the phase shift we see, this is x plus 90. That's the same as x minus negative 90. So you can say negative 90 degrees, or if you say to the left by 90, that's going to work also. And so that's how far the graph is going to end up being moved. And so now we've got to figure out how to do this, how to do a graph that does these things. I've got a positive cosine graph, amplitude of 2, period of 360 degrees, move to the left by 90. Now there's a lot of different ways that we could do this, and if you've got a way that works for you, go for it. But I'm going to go through this and try to make sure that everyone understands the process for this. I'm going to start by saying that if this phase shift is going to move it to the left by 90 degrees, the way I graph a cosine function, I'm always thinking about where it starts. And now the place where it starts has been moved to the left. So when I graph this, I'm actually going to put my y-axis a little bit over to the right so that after it's been shifted, I can still see the quote beginning unquote of the graph. As far as the period of 360 degrees, that just means we'll be able to lay it out like I've been laying it out. I'll just mark off on these intervals. And as long as I'm consistent with the way that I've been doing this, I should be able to see at least one full cycle of the cosine curve. In 4 of these intervals, that's 360 degrees, like always. Well, like it is if that's my period. So by making this the length of the period, I know that I'm going to be able to see a full graph. And I'm just going to fill in the rest of these like this. Amplitude of 2, we just go from -2 to +2, no problem there. And then finally, if I want to move this 90 degrees to the left, I'm going to think about my positive cosine graph normally starts over here, but it's been shifted to the left by 90 degrees. And so I'm going to do this a couple different ways for you. One way to think about where these points are is to think on an individual basis. The points were at +2 and then 0 and then -2 and then 0 and then +2. I could think of that point that was at 90 degrees crossing the axis has been moved to the left by 2, or excuse me, by 90 degrees. The point that was down here at 180 has been moved to the left by 90 degrees. And I can think of it like that. The one that was at 270 crossing the axis is moved to the left. At 360, moved to the left. And there we see most of the curve. I'm going to fill in the rest of these, the significant values, the 1/2 that's been stretched out by a factor of 2, and then I have to put the graph that looks like that. Another way to think about that is once I figure out where it starts, we can follow that same pattern and fill in the rest of them. And all we really need to think about with that 90 degrees is that initial shift, but then the shape of the graph stays the same. The size of the graph relative to the axis stays the same. So kind of interesting that what we have now, the result, we know that this graph came from a cosine graph that's been shifted to the left by 90. But if I didn't show you what this equation was, if I slide this over here and ask you what this equation is, you could also say, well, that looks like a sine graph that's been flipped upside down. This looks like y equals -2 times sine of x, or theta. And so just worth noting that these transformations could end up with graphs that may look similar to other graphs. All right, next one I want to take a look at, we're going to switch over into radians. Notice that this one is in factored form. The 2 has been factored out for you. On your homework assignment, you're going to have to do a lot of the factoring, and I'll do that for my next example also. But in this case, baby steps here, I am going to go through and figure out my different properties. My amplitude is 3. That's the number that's in the front. The period of this graph, because that 2 has been factored out, this was a 2x. My phase shift over here looks like it's in radians, so I'm going to do my period as 2 pi divided by the k value. In this case, it's 2, and so the period of this graph is pi. I'm not sure why I made that so small. And then finally, my phase shift, I'll just use PS to stand for phase shift. My phase shift, this is plus pi over 3. So if you want to tell me that this is a negative pi over 3, or if you want to say to the left by pi over 3. Pi over 3 is not good enough. If you say the phase shift is pi over 3, I will assume that you mean a positive pi over 3, which means moving to the right. And we don't want that. This is a negative phase shift. This is x minus negative pi over 3. This graph is going to be moved to the left. If you're doubting that, go back and watch the first 6 minutes of this video where I go through on Desmos and show you how that works in the equation with x minus. In any case, there we go. I've got my amplitude, my period, my phase shift, and we're ready to go. Now, on this one, I'll do the same thing. I've got a shift to the left. So I am going to make my axis over here a little bit to the right of where it was, so that I've got room to build over here. I'll mark off my graph in the same way I always do. Oops, I'm going to make these blue to be consistent with the slides that I've got ready to go. I suppose it doesn't matter too much. And then vertically, we know this is going up 3 and down to -3. My period is pi, so 1, 2, 3, 4 intervals. I'll mark off. There's my pi. Half of that is pi over 2. Half of that is pi over 4. Excuse my sloppiness. When I go to the next slide, it'll clean this up a little bit, but I wanted to talk about how we're going to determine this phase shift. Pi over 3 is my phase shift, and it's hard for me to see what a pi over 3 looks like on this graph. And so here's one way to think about it. And I'm going to say, how about this? If this was not an honors level class, I would probably just say something like, just plug it in your calculator. Take a look at what pi over 4 is. Take a look at what pi over 3 is, and you can make a pretty good guess as to what it looks like. But because this is an honors level course, I want you guys to be able to think about stuff like this. I'm going to go down on a smaller level and say that if this is pi over 4, then each one of these dotted line, each one of these vertical grids that I've got here is 1/3 of pi over 4. Each one of these is pi over 12. And so now the question is, how many pi's over 12 do I need to make a pi over 3? This is 1 pi over 12, 2 pi over 12, that'd be pi over 6. 3 pi over 12 is pi over 4. 4 pi over 12, hey, 4 pi over 12, that's pi over 3. So on this grid, counting off by pi over 12s, I determined that 4 of these grid lines is the equivalent of pi over 3. And so I'm going to move back over here and we can get this thing laid out. Pi over 3, I just determined, is 4 of my grid lines. And so I'm going to take this pi over 3. I've got a positive cosine graph. I'm going to take that point that was normally up at the top, and I'm going to move it over 1, 2, 3, 4 of these grid lines. That's what my pi over 3 looks like. And so the place where it would have been crossing down here at pi over 4, I'm moving that 4 units over to the left because that's what pi over 3 looks like. And then fill in the rest of these dots like I normally would, either by looking at them relative to my graph or taking points and moving them over by that same pi over 3. I will do the same thing that I always do around the places where it crosses the axis. This helps me to make my graphs not look too bumpy, and I would recommend that you do the same thing. Some of the graphs that I'm seeing on your homework are a little bit zigzaggy. If you've got line segments, then you don't have a sine curve. You've got, well, I don't know what it is, some periodic zigzag graph. And me talking and graphing is making my graph look a little lumpy, so I'm going to skip ahead and go with the slide that I made before. But that's where that comes from. We know that this is a cosine graph that's been shifted over by pi over 3. And there we go. That's how I graph this one. It's too bad I'm not in the classroom with you. I could say, does anyone have any questions? And I'm sure lots of people would say, how did you figure this part out? But instead, I guess I'll have to go through some examples. I hope I'm explaining this well, so you can go back and rewatch stuff if you need to. But let's move on. Ooh, got another cosine. Okay, the next one's a sine graph. But I do have another cosine for us to do right now. And this one is not in factored form. So I've got work to do before I can look at this. The phase shift is not going to be pi over 2. Do not be fooled by that. This is not in factored form. We need to get this thing into factored form in order for us to figure out what the phase shift is. The amplitude is 25. No problem there. The period of this graph is going to be 2 pi divided by 2/5. Everything else is okay. But I need to figure out what the number is going to be here that is going to reveal what my phase shift is. So 2/5 times something would give us that pi over 2. And the way we're going to figure this out, I'm going to think of this as when I factor out that 2/5, I'm dividing everything in the parentheses by 2/5. So I'm going to take that pi over 2, and I could say divided by 2/5 down here, but I'm going to skip ahead and say that dividing by 2/5 would be the same as multiplying by 5/2. And so I've got 5 pi over 4. That is my phase shift. And when you're doing this factoring, if you're not sure if you've done it right, you can always check your work by redistributing. If I distribute this 2/5 over these parentheses, I've got 2/5 x, good, minus, let's see, we would have 10 pi over 20. 10 pi over 20, that'd be the same as pi over 2. So there we go. I've got an amplitude of 25, a period of 2 pi over 2/5. Ooh, I suppose we got to figure that out also. So 2 pi divided by 2/5. I'll do this here also. Instead of dividing by 2/5, I'll multiply by 5/2. 2's cancel out, and looks like I've got a period of 5 pi. And then finally, a phase shift of 5 pi over 4, or if you want to say to the right by 5 pi over 4. Do not say negative 5 pi over 4. That tells me that it's moving to the left, and I want to make sure that that you're clear about that. Again, phase shift of either 5 pi over 4, or if you want to just clarify and say 5 pi over 4, if you want to say to the right, that'd be okay also. If you just say 5 pi over 4, I'll assume that it's positive 5 pi over 4, and that would be okay. But if you're worried about me understanding what you're trying to tell me, go ahead and tell me either left or right. So here we go. I've got my graph in both unfactored and factored form, like we found. On this one, because it's a shift to the right, I'm going to go back to putting my axis, my y-axis, way over here on the left, and then I'll show you how I deal with the shift to the right. First things first, let's mark off. I've got a period of 5 pi, so I will get my blue pen and do the usual marking off. I'm going to mark 4 intervals. That's what 5 pi looks like. I'll put another interval on there for good measure. Half of 5 pi is, well, 5 pi over 2. Half of 5 pi over 2 is, ooh, look at that, 5 pi over 4. And that just happens to be what our phase shift is, which is both convenient and pretty common for us to see. So each one of these big intervals is a 5 pi over 4. This is 5 pi over 4, 10 pi over 4, 15 pi over 4, 20 pi over 4, and 25 pi over 4. And again, this is a little bit sloppy, but it'll get cleaned up on the next slide. And then I'm going, my amplitude is negative, excuse me, I almost made an embarrassing mistake to say that an amplitude was negative. Of course, the amplitude can never be negative. The amplitude is positive 25, so our graph's going to go from negative 25 to positive 25. So there we go. I've got a graph scaled, ready to start labeling points on here. I've got a negative cosine graph. So that negative cosine graph would normally start off down here, but I've got a phase shift of 5 pi over 4 to the right. So that point that would be starting way down here on the bottom is moved over to the right by 5 pi over 4. Again, this is a negative cosine curve. So it would start over here at the bottom of the graph, and then it's been moved over by 5 pi over 4. The point where that graph would have crossed the axis has been moved over by 5 pi over 4. And then at this point, I'm just putting the dots in the same order that they always go. Middle, top, middle, bottom, middle, top, middle, bottom. Looking at the graph, this one must be over here on this side. And then I'll fill in my halfway values. And so playing connect the dots, we see what this graph is going to look like, and I'll skip ahead to after I've played connect the dots to get something that looks like that. Lots of stuff going on here. If you don't feel proficient at dealing with the amplitude, go back to last week. I think that was on Tuesday, or maybe it was even on Monday. Become an expert at amplitude, and then once you're an expert at that, move on to the period, and once you're an expert on that, then start doing the stuff that we're doing now. But if I don't know if this is true for anybody, but if you just skipped the first few lessons and decided that this is where you're going to start this chapter, it's going to be tough because there's a lot of stuff happening. But dealing with the amplitude just by simply scaling the graph, dealing with the period by scaling the graph horizontally, and then finally adding the phase shift, and all of our graphs end up looking, well, hopefully similar. Okay, one more example for us. I'm not sure how long this has been so far, but I feel like this is, I've tried to choose problems that are different from each other. We'll do a sine graph. We haven't done any sine graphs today. We'll go back to degrees for this one. Starting with the amplitude. The amplitude is the absolute value of the number, the coefficient in front. So the amplitude is positive 6. Of course, The amplitude can never be negative. How embarrassing would that be? The period of this graph is 360, either 2 pi or 360, but since my phase shift is 240 degrees, we'll go with 360 degrees divided by that 120. 360 divided by the k value, and looks like the period of this graph is going to be simply 3 degrees. I'm being picky about this. I'm going to call that 3 degrees. If you just call it 3, no one's going to be upset about that. And then finally, my phase shift. Ooh, I need to get this into factored form. If I factor out that 120, x minus something, same idea. Either look at this and say 120 times what would be 240, or think of this when I factor out that 120, we're factoring out by dividing that from both terms. So 240 divided by 120 gives me the phase shift of 2. And again, positive 2 is fine. 2 to the right is fine. Negative 2 is wrong. I know that it's x minus 2. It looks like a subtraction. Well, it is a subtraction, but it's not a negative. We're subtracting a positive number, either 2 or 2 to the right. And then let's start figuring out what the graph is going to look like. Same as always, when I've got a shift to the right, I'm going to put my axis over here on the left side. I'll count off my intervals, 1, 2, 3, 4 intervals. And that gives me my period of 3 units. So this is 3 halves or 1.5, 3 halves or 1.5, either one's going to be fine. Half of 1.5 is 0.75, or if you call that 3/4. But that tells me we're counting by 3/4. So either 0.75, 1.5, 2.25, or if you did 3/4, 6/4, 9/4, 12/4, 15/4, or decimals are going to be fine on this also. I'm going to skip ahead to the slide where I have stuff labeled already. Up from -6 to 6 because my amplitude is 6. My horizontal scale has been taken care of because I knew what the period was. I'll see one full period of this graph, at least one full period. And then finally, I'm moving 2 to the right. So here we have the same dilemma. If this is 1.5 and this is 2.25, where exactly does that 2 go? If this was a regular level functions in trig class, I would say, well, if 2.25 is there, 1.5 is there, then just somewhere in the middle, not a big deal. And it's not a huge deal, but in this case, because of the way that I've got this thing scaled, I can see that if this is 0.75, well, then each one of these is 0.25, 0.25, 0.5, 0.75. This one is 1, 1.25, 1.5, 1.75, and there's 2. 2 units on my scale looks exactly like this. I must have 8 of my intervals is what 2 looks like. So as I make my graph, I've got a negative sine curve. So normally that would be crossing at the axis and decreasing, but that point where it was crossing has been moved to the right by 2 units all the way over to that point. I'm going to make that dot really big so that we don't lose track of. That's where this graph started. This point is where my negative sine curve is beginning. So again, because it's negative sine, this is where it's crossing the axis and it's going in the negative direction. The spot over here at the end of my first interval where it would have been at the bottom, that's been moved over by that same 2 units. So it's going to move from 0.75 all the way over to 2.75, which would be right there. The point here where it would be crossing but increasing has been moved 2 units. So at 3.5, that point would be right there. And now I'm starting to see where these, where the rest of these dots are going to go. And this is, again, you've been getting practice. Hopefully you're getting good at this. The shape of these graphs stays the same. The number of intervals that I'm counting to figure out where these points go is staying the same. And I end up with a graph that's looking like this, playing connect the dots. I'm going to skip ahead to the one that I've got prepared and ready to go. And there it is. I've got a negative sine graph shifted to the right by 2. Notice that this could look like a positive sine graph shifted over by 0.5. In fact, maybe that's worth me typing out. This looks exactly the same as if I had a positive sine graph. I'm going to go positive 6 times sine of, let's see, same period, but maybe it's been shifted over by 0.5. Oops. Instead of 2, these two graphs would look identical. And if I gave you this graph and said, write the equation for this graph, most of you would probably give me this one, because you'd say amplitude of 6, no problem. And that point where it crosses the axis, but it's increasing, it's been moved over by 0.5, make it x minus 0.5, and that moves it over to the right by 0.5 degrees. All right, so there we go. That's my last example for today. Hopefully that's helpful. I would imagine, and I would not be surprised if some of you need to go back and rewatch this one. We're starting to get to the point where there's a lot of stuff going on, a lot of stuff to keep track of. Fortunately, we only have one more thing to add. Tomorrow, we're going to be adding a vertical shift, so sliding this graph either up or down, and that's going to take care of all the different transformations that we can do to these graphs. But I will save that for tomorrow. In the meantime, good luck on the assignment. A few of you have been communicating with questions through emails, and I've been doing some Zoom meetings with people. If anyone else needs that, certainly get in touch with me. Otherwise, good luck with this assignment, and I will check in with you again later. Bye-bye.